Welcome back to Understanding Python. My name is Jake, and today we'll be jumping into metaclasses. We'll start by exploring how Python actually constructs your classes, then use that foundation to understand what is really going on in metaclasses. If you watch the rest of my series, you'll be able to follow along just fine. As we go, if you learned something new, let me know by liking the video. Now let's get started. To start off, I've created a very basic class called example. The contents of this class really aren't important, but it'll be a good way to show you when particular parts of a class are being executed. To further illustrate this, I'm going to add in a bunch more print statements and bring you back when I'm done. Alright, so as you can see, I added print statements at the outer level of the class body, added some print statements inside dunder new, dunder init, and then two more statements out at the class body itself. So with that in mind, let's go ahead and load this file and see what happens. Okay, we see that right away we have a number of print statements. We see the print statement here, the beginning of example class definition. Then we see the class var itself with a value of test. We don't hit anything in the dunder new or dunder init because those aren't at the outer edge of the class boundary. And then we also have middle of example class definition. Again, nothing for example func, and end of example class definition. That's because what's really happening when Python loads a file is that it executes the contents of your class body. So all of these statements will actually be executed at runtime. It will then create the dunder new, dunder init, and example func functions and load them into the class itself. Additionally, any other statements that are at the class body level are also executed. So let's see what happens if we go to create an instance of the example class. Give ourselves a little bit more room. Here we see we have entering dunder new. Then we have the arguments that are passed into dunder new. The first being the class object itself. We have no args being passed in, and then the keyword arguments that we passed in to the example. After that, it gets passed into dunder init, and then we print the contents of our dunder dict. So not only does our instance have a dunder dict, our class itself also has a dunder dict. And in that dunder dict, we have not only the module, we have our class variable here with its value. We have the dunder new function, dunder init function, our example function, and then the dunder dict, a weak ref, and a docstring. Furthermore, the type of our example instance is dunder main.example. But what would be the type of example? Well, that's type. How about the type of type? That's type again. Type is actually the bottom of the chain here because it's what Python uses to create classes themselves. And we can do this manually a couple ways ourselves. Let's exit out of here and move on to the second example. So for this, what we're going to do is we're going to create this class a lot like Python would itself. So remember how I said that Python executes the class body? Well, let's do the same thing. Let's take the code that's in that class body there and store it in a value we'll just call class body. There we go. A direct paste of everything that's in that class body. Now, the order that Python does this is first it needs to create a namespace for your class. And for that, we can use types methods ourselves. So type.dunder prepare. We're not going to give it any arguments. And what this is going to create is considered a namespace, but it's effectively just a dictionary. Next, what we're going to do is we're going to call exec to execute the code in the class body, giving it access to any globals So if we had any specific imports that our class body needed, it could use those imports. And we're going to execute that into namespace. And finally, we're going to create an example2 class by manually calling type as a class constructor. A lot of people don't actually know that type can do more than just return the type of something. Most of the time that type is actually used is under the hood in Python to create classes. So what we're going to do is pass in the name of the class, any base classes. If you had something that you wanted to inherit from, you could add these here as a tuple. So if we had like parent 1 and parent 2, we could add them here and then have proper inheritance. But for example, we're not going to have anything. And then finally, we're going to give it that namespace that we created before and executed the class body into. Now, if we load this file in IPython again and give ourselves some room, we'll have the example class go, and we'll also have example2 class go. And they should behave exactly the same, with one caveat, which I'll get to in just a second. If we create an instance of example1, we'll see exactly the same behavior as you saw before. And if we try to create one for example2, we get something interesting. So this is a limitation that we found here. It says superclass cell not found. And that's because of a little quirk in the way that Python 3 works as compared to Python 2, if any of you have used that before. So in Python 3, we can use this nice shorthand super annotation, right? Well, that's only because in Python 3, the compiler will, at runtime, inject the long form version of super into your code. Now, this isn't something that happens because we're not compiling it right now. We're executing the code directly. So we'll need to act like the compiler and put example2 and class. Now, if we reload this, see the same thing before, and now we can create an instance of example2 just by putting in exactly what that needed. So let's actually try to do this manually. So what I'm going to do is I'm going to comment out this section here. And if we reload this, we see we only have example class 1 that gets ran, but we do have class body. So that's a nice ugly form of our class body. Let's go ahead and run through the steps that we did before, where we say namespace is equal to type under prepare. And let's see what namespace actually looks like. It's just a dictionary, right? But when we execute the contents of class body, giving it the globals into namespace, what happens? Namespace looks like this. Now that's really similar to what we saw before, right? Let's look back at this. That's pretty similar, isn't it? So it has class var, test. It has dunder new. It has dunder init, all functions, example func, all functions. So let's pass this in to our creation of example2. All right, now we have example2, whose dictionary looks basically the same as before. The difference being that on top of class var new init and example func, class var new init example func, we have module dict weakref and doc added. So basically what Python did is it took that namespace dictionary that we had before and used that directly to create the class, adding in a bit more information to the dictionary and creating the overall class object. Not too bad, right? So at this point you might be asking, can I just create a dictionary as a namespace and then piece together things that I want inside my class? And the answer to that is absolutely yes. So we'll create method 3. So for method 3, we're just going to create an init method, which is going to basically do the exact same thing as we had before. So let's just copy that directly from here. As a matter of fact, let's just copy this directly and strip out what we don't want from it. Adjust the formatting a bit. We'll just call that init. I'll leave that the same. Get rid of that print statement there. Next, let's create a namespace dictionary manually. Let's not forget to add in our class var, whose value is equal to test. Again, another attribute, just a thing in a dictionary, right? Under init will map to our init function up above. An example func maps to, you guessed it, example func. And then creating our example3 class is as easy as this. It doesn't have any parents, and we'll pop in namespace. Not too bad. And if we load this, we didn't print anything for our third class. However, we should see, yep, here we go. Example3. Basically same dictionary as we saw before. And can we create an instance of it? We sure can. And that behaves exactly the same as before. So as you can see, when you're creating a class by writing out in the traditional way in Python, what's really happening under the hood is that Python is evaluating your code. In the case of super, as we saw, it's also injecting some of that information in there. It's then creating a namespace, executing your class body. As we saw with all those print statements, it's actually executing the code in there, and the results of that execution get put into the namespace that I created in the previous step. From there, it uses type, again, to actually construct your class itself, giving that class name. If you passed along any parents, it's also going to be in there. And then the namespace that it executed the class body into. You know, outside of just metaclasses themselves, this is also important to keep in mind when you're creating classes, is that anything that you have at the class level is going to be executed. So if you've seen some peculiar behavior around some classes that you defined, where things were happening that you didn't expect it to, there's a good chance that this is the reason why. At this point, you may be asking yourself, okay, so we've called type.prepare and we've called type here to create classes, but we still don't know what's actually happening within those methods themselves. Like, how can we control what happens in prepare? And how can we control what happens when type is actually creating the class itself? Well, my friend, you are in luck, because that is the meat of this video. That is what metaclasses allow you to do. So the very first metaclass that we're going to get into, we're going to call noisy meta. Now, noisy meta, like all other metaclasses, need to inherit at some point from type. The vast majority of metaclasses do inherit from type directly. However, you might encounter a really weird project where it has multiple metaclasses layered on top of each other. If that ever happens, please leave a comment on this video with a link to the source code, because I'm really interested to see what exactly is going on in that code base. So in this metaclass, there are 4 key dunder methods that I'm really interested in looking at. The first one is going to look really familiar at this point, and that is called dunder prepare. So the exact same thing that we used to create the namespace before is what we're going to use in our metaclass, so we can take a peek under the hood. Its method signature looks like this: meta, name, and bases. What is meta a reference to? Well, this is actually a class method. So meta is the meta class itself. Since we don't really actually want to interfere with this, what we're going to do is we're going to capture the namespace object that's created when we call super dunder prepare, passing in the name and bases again directly. And then we're just going to return namespace. I'm going to keep this nice and clean for now, just so we can see what the class looks like in a minimal form before I muddy it all up with a bunch of print statements and make it actually noisy. The next one is going to be actually a static method. And that's because it's going to be dunder new. So this again is going to take in a meta class. It's also going to take in a name, the bases, and the attributes. Next, we're going to store the result calling super dot dunder new, basically passing in exactly the same thing as we took in. And then we're going to return that result. Again, we'll be adding a lot more print statements here in a little bit. And then there's two more dunder methods that I'm interested in. It's going to be dunder init, this being class name bases and adders again. And you likely guessed it. We're going to store the result, calling super, passing in that name, bases, and adders, and then return it. And then the last thing we're going to get into is dunder call. Dunder call isn't something you see used often, but it may be useful in our examples. And again, in the minimal form, this is going to look a bit boring, but we're basically just going to be passing everything over to our super call and then return that result. All right, so this is the actual functional base of our Metaclass. Overall, because it's not really doing anything, there's not much to it. But once we add the print statements, we'll see all of the data that's being passed around, and then you'll be able to see exactly what's available to you if you want to develop metaclasses of your own. Because you can modify behavior in any of these methods once you know what's being passed around. I'm going to go ahead and make this very noisy, and I'll be back when I'm done. Alright, so right now we have a very noisy Metaclass. It's got print statements everywhere, detailing everything that's going into each method and everything that's going out of each method. So let's see what this looks like. In order to do this, we're going to modify our original example class and specify Metaclass equal to noisy meta. And for the sake of organization and the fact that we can't reference noisy meta before it's been defined in the file, what we'll do is we'll copy this class and then we'll comment out all of the previous classes before and pop our example class right down here. Now it can inherit as meta class, which is noisy meta, and be perfectly fine. So let's go ahead and load that. Okay, here we go. I've scrolled to the top of noisy meta and we can follow along in the file. We see once the file is loaded, the very first statement that we get is that we're entering dunder prepare. That's because noisy meta has already been evaluated. So at this statement, Python is starting to read through our example class. Just like before where we said namespace is equal to type.dunderprepare. That's basically what Python's doing here. So it's calling dunder prepare. We see that, as I said, the meta argument is indeed our noisy meta class. And then our line where we have preparing name with bases, we see preparing example with bases. Again, since it didn't inherit any parents, there were no bases there. If we did have some parents, then we'd see them listed into the bases. Then on line 79, we see that our namespace, again, it's just a dictionary because this is the output of dunder prepare. Now, interestingly enough, what's the next thing that comes up? It's not dunder new, it's our class body print statements. Because remember, again, Python's executing the class body into the namespace. So in these 4 lines, we see Python executing our class body, just like we did up here. Executing the class body with the available globals into the namespace. So by the time that we get down to entering dunder new, our namespace should be populated. And maybe we'll see that. Again, we see that the meta class is still noisy meta. And then our line where we see creating name with bases and adders, we see creating example with bases, Again, just an empty tuple where our parents would be, and adders. Now this is something interesting. Look at adders. Adders is everything that I'm highlighting right here. That's a dictionary. And what's the contents of that dictionary? Exactly what we saw in the namespace. That's because the adders here is just the namespace. As a matter of fact, if we wanted to, we could rename that namespace. We'll keep it as is. And then we get the result back. And the result is the example class object itself. So, super new created the class object using the name that we passed in, the bases, and the adders, or the namespace. Name, bases, and adders. That's exactly what we saw when we called type directly. The name, the bases, and the adders, or namespace. So dunder new is the first thing that happens here. And following up immediately from dunder new is dunder init. Not only is it creating the class object itself, it's also initializing that class object. So we have entering dunder init, we print the class, we see that we have our example class. We're calling initializing name with bases and adders. So we have initializing example with bases, again, don't have any parents, and then adders or namespace as we'd expect. So what about this dunder call method? When are we going to get that? Well, when do you call a class? You call a class when you create a class instance. So we see here, entering dunder call. We see the class that's being passed along. We see that we're calling class example with args. And I have a typo here. Instead of keyword args, it's apparently LWArgs. But these are the arguments that were passed in right here. And now we see that we are executing not only the dunder new for example class itself, but also dunder init. And then we get the result back, which is that class instance. So dunder call is another good place that you could modify behavior of class instantiation, because you can intercept the arguments and the keyword arguments that are being passed into a class before it even reaches that class's dunder new method. And depending on the results, you could also intercept that class on the way out before it's returned to a user and modify it in some way or another. So dunder call is often overlooked in a lot of metaclasses, but in my opinion, it's one of the more powerful methods available. Okay, so next up, I want to show you a few simple metaclasses that show you some of the more functional things you can do with them. Some fairly powerful things you can do. For the first one I want to play around with, we're going to need to import one of my favorite modules in all of Python, and that is inspect. In this metaclass, we're going to call it auto slots. I don't believe I've touched much on slots, and they're not really very important for this example, and we'll show a little bit of the behavior as we're testing this. So don't worry about what slots are just now. We'll talk about it a bit. So we're not going to override anything in dunder prepare. Instead, we're going to override dunder new. Again, we're going to take in the meta, the name, the bases, and the adders. Remembering that those adders, basically just that namespace dictionary. So what we want to do here is check to see if they defined an init. Because if so, we can do a little bit of magic in here with inspect to pull out exactly what I'm looking for. And don't worry too much about that line right now. It'll become a little bit more apparent as we start testing this. So we're also going to want to print out what we took from slots, and we're going to add on to the adders themselves a slots attribute with what we pulled out. Simply pass that back up to the main type class, passing back in the meta, the name, bases, and the adders. So we're keeping everything else the same, except we're populating a slots attribute. Now, the test for this will be a class called test slot. We're going to specify our metaclass is equal to auto slots. We have a dunder init, and this class is real simple. It's just going to have an A, B, C, arguments, and simply say self.a is equal to A, self.c is equal to C. So let's jump into this file and take a look at what's going on. Okay, so loaded the file, and we see slots is equal to A, B, and C. That's because what this line is doing here is using inspect, look at the signature from dunder init, specifically the parameters that are defined in this section, and even more specifically, the keys themselves. That's self, A, B, and C. And this little last part here says we want to skip self because we don't want to add self to slots. So we're adding A, B, and C to slots. And that's what we see here. Slots is equal to A, B, and C. We set that on the class. So if we look here, test slots, we look at dunder slots, A, B, and C. So what does this mean? Let's create an instance of test slots. We have ts.a is equal to 1, 2, and C is equal to 3. In any of these, if we wanted to modify them, say B is equal to 15, ts.b is equal to 15, right? But what if we wanted to set ts.d equal to, say, something like 7? That's not going to work because slots limits the attributes on a class. There's a lot that actually goes into slots themselves, but if we were to look here, we were to see that this instance object doesn't have a dunder dictionary. So for those of you that are familiar with slots, if you wanted to have them created dynamically based on whatever you pass into dunder init, you can absolutely use an auto slots metaclass. We might dig more into exactly how slots works in a later video. And if you are interested in that, then please leave a comment to let me know that. But I want to do one more example before we go. And this one might be a little strange. We don't have to import anything for this because overall the functionality here is fairly simple, which you may be able to infer from the name itself. Again, we'll be using dunder new for this. Modifying dunder new might be the more popular way to use metaclasses. Takes in the same arguments as before. What we're going to do here is we're going to do a little bit of inheritance type magic. So I'm going to go ahead and write this out and explain it afterwards. All right, so this metaclass is a little quirky. So basically what it does is the reverse of an abstract base class, where in an abstract base class, you can define methods that you must override. Otherwise, you raise an error. But for no override, it works the opposite way. So children can't override methods that a parent class has already defined, unless that's a dunder init method. And the way we do this is we iterate through all the parent classes that this particular class may have. Then we iterate through all the adders, or everything that's in the namespace. If the name of that doesn't start with dunder, and the parent class has that attribute, then we're going to raise the type error. So for the sake of time, I'm going to take some classes out of the oven. So here we have a parent class, which inherits from the metaclass. Now, one thing that's neat about metaclasses is that if a parent inherits from that metaclass, then all the children that inherit from a parent also inherit from that metaclass. So they inherit that same metaclass behavior. So in this parent, we have dunder init, just as usual, and we also have a test func defined. Now, the good child isn't overriding test func. It's actually writing a new function. But the bad child is trying to override test func. And we'll see exactly how this plays out for him. When we tried to load the file, we saw we get a type error, class bad child. And we see the type error, bad child.testfunc can't override parent.testfunc. So here we're forcing a no override behavior on child classes. So our metaclass that forces that no override behavior is working perfectly fine. And that wraps up this video. Now that you understand how classes are constructed and the role metaclasses can play in that construction, take some time to find examples of metaclasses and trace their execution flow. If you have any further questions or recommendations for others, leave a comment down below to let me know. As always, today's code will be added to the Understanding GitHub repo, so check the description for a link. And of course, if you have any questions or suggestions for topics you'd like me to cover, let me know in the comments section. To keep up with this series, please consider subscribing. Thanks for watching.